Hey there, chemists. In this lesson, we are going to look at some trends that we observe across the periodic table as we go one row left to right and as we go down a column top to bottom. And I actually want to kick it off by looking at what types of things can we expect to see in terms of the different reactivities. And the best way to show you that remotely is via a video. So this is a short video that walks through the reaction of alkali metals as we go down the column with water. So there's a small piece of lithium metal. These are the pure metals, and this is lithium metal in a dish of just water. You can see that it quickly effervesces, it gives off a gas, and all the alkali metals do this. They form the metal hydroxide and hydrogen gas. Sodium metal reacts even more quickly, giving off the same hydrogen gas. Potassium metal, you'll see, reacts even more violently. This time the reaction is so exothermic it actually ignites the hydrogen gas that's formed, and you can even see a violetish flame due to the potassium ion. Rubidium is even more reactive. Just a small amount of it goes into the water and it reacts very quickly and very exothermically. And then I believe they put a sample of cesium, the fifth alkali metal, as you go down the column of the table, but it doesn't last very long, as you'll see. There we go. And it doesn't even survive, if that's accurate. So what are some things we can use to explain about the properties of the elements that might explain why we see these differences in reactivity? And that's what we're going to get to today. The first trend I want to discuss is the size of the atoms, the atomic radius. And if you look at what's on your screen right now, you can see that the smaller atoms are in the upper right of the table and the larger ones are in the lower left. And it's worth noting, I think, that most people say helium is the smallest. Helium's radius is measured by what's called its van der Waals radius, which is based on multiple helium atoms and the van der Waals force they exert, as opposed to some other atoms like hydrogen, which can be measured with the half of its average bond length. So different things measuring to say the same thing. It's actually sometimes hard to compare the radius. You'll even see different books disagree about who is smaller, hydrogen versus helium, but most sources I've checked say helium, so I'll also say that it's the smallest one. For the most part, as you go across the table, the radius decreases. Radius decreases across a row, and it increases down a group. Now, any 10th grade chemist can recite that, but we're going to say why. Actually, most 10th grade chemists can also say why. The reason it gets smaller as you go across the row is because you have a greater effective nuclear charge. That's a fancy way of just saying there are more protons. So the given outer shell of electrons is pulled in that much more strongly by the greater nuclear charge. Yes, there's more electrons as well, but they're all going into the same valence shell. And they're all getting pulled in by this larger nuclear charge, more positive charge attracting those extra electrons. However, when we go down a group, something very different happens. It gets larger, and this is because of more what's called shielding. Now, a shielding effect means there's more energy shells. I'll say more shells. And what you have is, let's say, some positively charged nucleus with electrons surrounding it. And then once you put electrons in another energy level higher than that, here's some electrons. They are shielded from the nucleus by these inner electrons. So these outer electrons don't feel the full effect of the nucleus. They are literally blocked. So they are slightly repelled by inner electrons. And as you go down a column of the periodic table, that shielding effect is larger and larger and larger because we're getting more and more principal energy levels from n is equal to 1 all the way down to n is equal to 6 and 7, etc. Now, in addition to that, there's some trends we should also know about the ionic radius as opposed to the atomic radius. First of all, if you have a neutral atom such as lithium and it becomes a cation, cations are always smaller. So when lithium becomes lithium plus, the atomic radius of lithium is about 152 picometers. The lithium cation is only around 78 picometers. And the reason for this, lithium cation is smaller than lithium, and that's true, cations are smaller than their parent atom, is because the valence electrons in the valence electron is in a lower principal energy level. Lithium is 1s2, 2s1, but lithium plus is isoelectronic with helium. It's only got energy levels, it's only got electrons in the 1s, and that's it. So they are much closer to the nucleus. The opposite trend is observed for anions. Let's say I have an iodine atom. When you become the iodide anion, it's actually quite larger compared to the parent one. 153 picometers becomes about 196 picometers. So the reason an anion is larger than the neutral atom of the same element is there is more electron repulsion in the valence shell. You've just added an extra electron to that same valence shell, so picture one of those orbital diagrams. Now they're being all forced to pair up instead, or even at least occupy the same shell, and electrons are all negatively charged. They're going to repel each other. And we'll be able to use these concepts of attraction and repulsion to actually explain all the remaining trends, or most of the remaining trends in this lesson. So we're going to come back to this time and time again. These are fundamental concepts. Speaking of, let's come back to that video that we just saw about the alkali metals reacting as we go down the table. They get more and more reactive. What that reaction is when it sees water is it's an ionization. Water actually strips an electron away from the alkali metals. And we call this the ionization energy. The ionization energy is how much it takes to remove an outermost electron from an element. It's always endothermic. You always have to add energy to an atom to get it to lose an electron. And in general, it increases across a row, and it decreases down a group. And the reason for that is almost the same as the reason that we use to explain the atomic radius. As you go across a row, you get more and more protons holding on to that valence shell, holding on to all the electrons, and it gets more and more difficult. It requires more and more energy to remove any one of those outer electrons. However, as you go down a column, the valence electrons are in a shell that's in a higher principal energy level, and it takes less energy to remove those electrons. They are farther from the nucleus. So it's almost the same reasoning as what we used to explain the atomic radius trend. But I want to go one step further with this and talk about successive ionization energies. When we say ionization energy, we usually mean just how much to take away the single outermost electron. What about removing multiple electrons, maybe all of them? This is called successive ionization energies, and they generally increase as you remove more and more electrons. For example, we can quantify this. Aluminum, becoming aluminum plus, has an ionization energy of 580 kilojoules per mole of aluminum. If I want to take away the second electron from the aluminum plus, that requires 1,815 kilojoules. I want to take away a third one, it's 2740 kilojoules per mole. But once I want to take away the fourth one, watch what happens. It jumps to 11,600 kilojoules per mole. So we're talking on the order of 600 kilojoules per mole to lose that one, another 1,800 to lose that one, another 2,700 to lose that one, and then almost 12,000 to remove one of these next ones. And as soon as I highlight that, hopefully you can see why there's such a big difference. This is over a 300%, this is around a 300% increase. And we can actually use this as a way of identifying what column of the table an element is in. More energy is needed to remove inner electrons. We stopped taking away electrons from the valence shell once we formed the aluminum 3 plus cation. You want to make aluminum 4 plus, that is a lot more challenging, requires a lot more energy to do it. So if I didn't know that this was aluminum, I could at least look at these numbers for successive ionization energies and figure out, oh, there must be something uniquely okay with the 3 plus ion that's formed. So this is probably in group 13 as a result. I don't know that it's aluminum for sure, but it could be one of those elements and nowhere else on the table, most likely. And you'll see plenty of practice problems like that. So that's the energy required to lose an electron. What about the opposite? What if I want to add an electron? That also requires energy. This actually is a release of energy. I should say that involves energy. It doesn't require it. It actually releases energy. This is called the electron affinity, and it's how much energy is released. These are almost always exothermic when an atom gains an electron. So electron affinity, in general, we're still talking trends, increases across a row, and it decreases down a group. But there are lots of exceptions to this, and what's more useful than knowing the exceptions, I think, is being able to explain any aspect of the trend and even some of the exceptions. There's a graph that more or less plots the electron affinities for the elements. You'll notice it gets more negative as it goes up the y-axis, so you release more and more energy as you go up that y-axis. So the halogens have the most negative electron affinities. They release the most amount of energy. We actually say that they have a large electron affinity, referring to the magnitude of the electron affinity. But there's lots of exceptions in this trend, and I want to point out just one and show you how we can use orbital diagrams to explain it. So let's look at the elements in the 2p row from carbon to fluorine, and I'm going to draw their orbital diagrams and at the same time give you the electron affinities. The electron affinities for carbon are respectively negative 122 kilojoules per mole. Nitrogen is negative 7 kilojoules per mole. It's barely exothermic. Oxygen is negative 142, and then fluorine is negative 328. So fluorine wants another electron a lot more than carbon does. That makes sense. It becomes a filled valence shell, and it's got more protons. That greater nuclear charge in fluorine has a greater attraction for an incoming electron, so you release a lot of energy. But this isn't a perfect trend. There's quite an exception when we get to nitrogen, and that's what I want to talk about. So to do this, let's look at the orbital diagrams for those 4 elements. Carbon is 1s2, 2s2, 2p2. Remember Hund's rule, fill the orbitals singly before they occupy. Nitrogen is 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. And then fluorine, 1s2, 2s2, and then 2p5. Now, in order to describe electron affinity, I'll put another electron just in a different color. So when we add an electron to carbon, it would go right there in the unoccupied 2p orbital, and that would release negative 122. That would release 122 kilojoules per mole. Nitrogen, the next electron would go there. It would have to pair up, and it only releases 7 kilojoules per mole. Oxygen would also have to pair up, but it releases more, 142. And then fluorine also has to pair up, but it releases more as well. So why does nitrogen break this trend? Nitrogen is lower. Nitrogen has a smaller electron affinity, I'm going to say EA, because of existing electron repulsion. And that's just a sentence that tries to show what we just saw. Look at, as you go from carbon to nitrogen, carbon takes that extra electron in an unoccupied orbital. Nitrogen, it has to sit next to someone else. It has to fill up an already occupied orbital. Nitrogen doesn't want that. Then you should be going, well, then what's up with oxygen and fluorine? They release more and even more energy. How come that repulsion isn't there? Well, it is there, The difference is that oxygen and fluorine have a greater nuclear charge, so it overcomes that little repulsion, and it only takes one extra proton to do that. So I'll point an arrow toward nitrogen because that's what we were just talking about, but then let's highlight the oxygen row here for a second and say O has an extra proton. Which overcomes this repulsion. Which overcomes this repulsion. Okay. The last trend to talk about is actually just a relative trend. It's called electronegativity, and we only see this between atoms that are forming a bond. But we've turned it into a trend that's unique to the individual elements on the table, but it's something that's only relevant when atoms are already sharing electrons. This is the ability of an atom to attract electrons when they're sharing them, specifically when they're sharing them in a covalent bond. So first, the trend. In general, electronegativity increases across a row and decreases down a group. And the reason for that is similar to the reasons that we've been saying already. It has to do more with the type of octet that it wants to satisfy. So this will become more clear when we look at bonding and actual molecules when they share electrons, but I'm introducing it here because it's still a trend. Make a note that fluorine is the most electronegative element on the table, highest, En. That really means it's the greediest for electrons. So if you're an atom and you have to share electrons with fluorine, you're not sharing equally. Fluorine is holding on to those electrons much more closely to its own center than whatever the other atom is when it's sharing them with fluorine. Oxygen is the second most electronegative element, sort of a tie between nitrogen and chlorine after that. And as we get farther and farther from fluorine, you get less and less electronegative. Makes sense. It's hard to even talk about electronegativity with the metals section of the table, but they have these numbers, so we'll still use them. And what this does tells us how unequally shared electrons are. This is called polarity, and this is what we talk about when we have a polar or a nonpolar bond. A bond is polar if the electrons are not shared equally. If they are shared equally, you get a completely nonpolar bond, such as the HH bond. This is totally nonpolar. They're completely covalent. But as we go down this list, I actually get to the most polar one. That's with fluorine, and the electronegativity, the polarity increases in that direction. Polarity increases. And we can tell about electronegativity and polarity based on the difference in electronegativity. A greater change in electronegativity, delta En, means a more polar bond. Okay, now we're going to come back to electronegativity later when we look at bonding in the next couple of lessons later on in this unit. But those are the trends that we should know for this course: electron affinity, electronegativity, ionization energy, and atomic radius. And we use a lot of the same concepts to explain those trends. I started off this lesson by showing a video with the reactivity of the first column of the table. I actually want to end by showing another video that shows the reactivity of the second to last column, because one trend we didn't talk about is reactivity. It turns out that reactivity really works toward the extremities of the table. The most reactive elements are up near fluorine or on the exact opposite end of the table, with the exception of the noble gases. Those are very, very stable elements, but you get very good reactivity in the upper right and in the lower left of your table. So to show that, let's see another video, this time of the halogen elements, and here they are. This shows the 4 halogen elements in their gaseous state. They're vaporizing. There's fluorine, chlorine, bromine, and iodine. You can even see the colors that the vapors give off. Bromine is notoriously red. Iodine is kind of a purple vapor in its gaseous state. Fluorine is fairly colorless. Chlorine is like a green gas. Bromine is actually a liquid at room temperature, and iodine is a solid. We'll learn why later on in the course. but they're all just diatomic halogens, and what we're about to see are the reactions of the halogens with different elements. They're usually quite reactive, and they all have a valence of 1. We look at their structures. So diatomically, they'd be F2, Cl2, Br2, and I2. They're just missing the subscripts. Fluorine reacts with everything. It's the most reactive element on the table. There's just a jet of fluorine and iron, and it immediately oxidizes it. There's a sample of charcoal or carbon immediately getting oxidized by fluorine. Here's fluorine and hydrogen in a balloon. They ignite it, and you get an instant fireball. The exotherm ignites it. There it is in slow motion, just to show the fireball more clearly. So fluorine reacts with every element. Here is chlorine, right below fluorine. Chlorine and hydrogen react with each other. These are two gases, and they form hydrogen chloride. The reaction is so exothermic, it ignites and gives you a flame as a result. But you can even slightly see, I think, the differences in color where the two gases meet and form a chemical reaction. Notice in the gas phase it's called hydrogen chloride. We only call it hydrochloric acid when it's aqueous. And it's about to become aqueous because the person in this video mixes it with water, and there we go. It sort of swallows a giant cylinder of water, just becoming aqueous from the gaseous state. Now this is aluminum powder reacting with fluorine, and it's very, very fast to react. So this is going to show us how the rates of the reaction are different. Here's aluminum in a column of chlorine. It reacts a little more slowly, but a bit more exothermically. You can even see the white precipitate of aluminum chloride. There's liquid bromine and a drop of aluminum, a piece of aluminum foil. It reacts a little more slowly, but you'll see a lot more exothermically as it starts to take off. We see a lot of vapors form as it heats up in exotherms, and the formation of aluminum bromide is quite spectacular. I'm not doing it live, that would be far too dangerous, so here's a video instead. Quickly takes on the infernal flames of I don't even know what. And then we're going down the table. We saw fluorine, chlorine, bromine. Here's iodine. Iodine and aluminum react even more slowly, but one would say more violently as it reacts. What you're seeing is a whole lot of iodine vapors coming off of this. So all the halogens react quite a bit and very differently from the alkali metals. And it's their electronic structure that we can use to explain those reactivities. That's what we're going to continue to get into in this course as we look at how molecules form.